Hello friend, in previous lecture we discussed thiourea base reaction. In today's lecture we will start the remaining part of thiourea base reaction. Now the thiourea catalyst, that means this L7 catalyst, this thiourea catalyst is being the 3,5-bis, that means this one, 3,5-bis trifluoromethylbenzene, that means this one, 3,5-bis trifluoromethylbenzene and dimethyl amino, that means these two groups, dimethyl amino groups has been relieved to be the efficient for the asymmetric Michael reaction of 1,3-dicarbonyl compound to nitroolefin. That means we call it as the scheme number 8. Now this methodology has been applied for the total synthesis of R negative balcopene. Okay, now here in scheme number 8, the reaction of 4-chloronitrostyrene, that means this one, 4-chloronitrostyrene and 1,3-dicarbonyl compound generates the quaternary carbon center with 94% enantiomeric excess. Reduction of nitro groups, that means here it is a simple the reduction of this nitro group to amine and subsequent cyclization. Here the cyclization will be take place. Subsequent there is cyclization and esterification, cyclization, and here the esterification and ring opening provides the R baclone, that means this one, baclopene, that means the here the simple here NaOH, ETOH, okay, then toluene and reflux. Here we get the 84%. Now then treatment with the HCl. Here again the ring will be the opening of this ring and we get the baclopene. Okay, that means this is the most important. When you use the thiourea catalyst, that means this L7 catalyst here, and this catalyst name as the 3,5-bis, that means this one, 3,5-bis trifluoromethyl benzene and dimethyl, that means these two group, dimethyl amino group. It is used as, that means this L7 catalyst, it is efficient for the asymmetric Michael reaction. This is 1,3-dicarbonyl compound and here the 4-chlorostyrene, that means the reaction between the 1,3-dicarbonyl compound and 4-chloronitrostyrene in the presence of this organocatalyst. Here we get the quaternary carbon center which having the 94% enantiomeric excess. Now then the simple reduction, that means NO2, there is a reduction in presence of the NaBH4. Here simple NO2 it will be the reduce and we get the NH2, and here the simple cyclization we get the this product, it having the 94% yield. Then on treatment with the base, here it will be converted into this the ester, it will be converted into the acid. Then here a toluene and reflux, it will decarboxylate, removal of this carbon dioxide. Here we get the 84% yield, and in next step on treatment with acidification, here again this ring will be opening of this ring will be take place, and then reflux, and we get the 38% yield of baclopene. Now the mechanism of above enantioselective Michael addition of acetyl acetone to nitroolefin catalyzed by thiourea base chiral bifunctional organocatalyst has been investigated using the density functional group theory, calculation, and results suggest that both the substrate coordinate preferentially. Here the transition states are shown. That means how this this L7 catalyst, it will be reacts with this 1,3-dicarbonyl compound. Here the simple intermediate steps are given. Now this catalyst, that means the bifunctional organocatalyst and this 1,3-dicarbonyl compound and nitroalkane, how they will be the react. Here the nitroolefin catalyzed by thiourea based chiral bifunctional organocatalyst It is investigated by using the density functional theory calculation, and it results suggest that both the substrate coordinate preferentially via bidentate hydrogen bonds. Here I mentioned here bidentate hydrogen bond. This is hydrogen bond. Okay. Now the deprotonation of the enol form of acetyl acetone. That means this one. Acetyl acetone by amine of the catalyst is found to occur easily here, and leading to an ion pair characterized by multiple hydrogen bonds involving the thiourea. That means here the multiple hydrogen bonds are involved. Okay. Now the two distinct reaction pathways have been explored toward the formation of Michael product, and that differs in the mode of electrophile activation. Both the reaction channels are shown. That means here both the reaction channels are shown here to be consistent with the notion of non-covalent organocatalysts in the transition state, leading to the Michael adducts are stabilized by extensive hydrogen bonded network. That means here in this picture here all three here are three hydrogen bondings are shown. Here only two hydrogen bonding. That means here these amine groups are not involved, and here all these amine groups and these remaining nitro groups with this hydrogen are involved. Okay, that means this is difference between these two transition states. Now the thiourea catalyze asymmetric Michael addition of activated methylene compounds to alpha beta unsaturated imides. That means this one alpha beta unsaturated imides have been developed. That means the scheme number 10 here the N alkynyl scheme number 10. That means here the N alkynyl 2-methoxybenzamide 2 here N alkynyl 2-methoxybenzamide is the best substrate among the corresponding benzamide derivative bearing the different substituents on the aromatic ring and react with the several activated methylene compound such as malonitrile, methyl alpha cyanate, and the nitromethane. Here we get the 93, that means the enantiomeric excess is up to the 93%. The reactivity can be attributed the intramolecular hydrogen bonding interaction between this NH bond of the imide and the methoxy group of the benzamide moiety. That means here this catalyst and this hydrogen bond are here involved. That means both these catalysts containing NH bond are involved in the hydrogen bonding. Here it is a simple reaction. This thiourea catalyze asymmetric Michael addition reaction of this activated, that means this activated methylene group. Why this is the activated methylene group? Because this methylene group is adjacent to the two cyanide group. Therefore, this is too much activated groups. Now then the addition of this activated methylene group towards this unsaturated imides group. Here the simple addition will be the take place, and here we get the 95% of this yield of this product. Okay, this is a dual activation of N alkynyl 2-methoxybenzamide, because here two hydrogen bondings are involved. Okay, here it is simple addition. Overall conclusion of this reaction, that means in presence of this L8, that means this organocatalyst. Okay, and here addition of this activated methylene, here if you add this alpha beta unsaturated imides, okay, and here we get the 95% of this yield. Here is the simple Michael addition reaction. Now the thiourea catalyst, that means his L9, this is thiourea catalyst L9 has been explored for the activation of quinoline with organoboric acids to facilitate the stereo control in the pitaceous transformation even at low temperature. That means here the temperatures are mentioned here minus 65 degrees Celsius. Now the quinoline, that means this one, the quinoline gets activated by the formations of N carboxybenzyl NCOBZ with the benzoyl chloride PHCOCl. The high degree of stereo control can be activated using the combination of these H2O and NaHCO3 as the additive. That means by using the NaHCO3 additives, here it activates the high degree of stereo control. That means here it is a simple addition when this quinoline is on treatment with the, that means here the first step it is protection of this amine, or here the simple reaction here nitrogen carrying, it is a pyridine type of nitrogen. Okay, now the nitrogen carrying lone pair, it will be directly attack on this here PHO C double bond OCl, here departure of this Cl, here we get the COPH. Now in next step there is addition of this boron. Okay, here take place at the alpha position, and here we get the 95% enantiomeric excess and 75% of this yield of this product. Here the different products are also given, and here the L9 is the organocatalyst are used. That means here the substitution of this quinoline molecule, we have to use this the organocatalyst. Okay, organocatalyst we call thiourea catalyst. That means we are mentioned here L9, and here activation of this quinoline with the organoboric. That means when we use the organoboric acids, the activation of this quinoline molecule will be take place at the low temperature, and the quinoline gets activated by the formations of NCOBZ. That means these two. Okay, with PHCOCl, here high degree of stereo control can be achieved by using the combination of H2O and sodium bicarbonate as additives. Now the domino, that means the thia-Michael reaction, thia-Michael reaction with the nitroolefin. That means this nitroolefin enolates provides the polyfunctionalization of chromine derivatives in a highly stereoselective manner in the presence of this thiourea. That means the is L10 organocatalyst. The three consecutive stereogenic centers here, that means this one, 1, 2, 3, 3 consecutive stereogenic centers, including the quaternary stereo center, can be generated with the high enantioselectivity. The catalyst, that means this L10 activates the nitroolefin. That means when you use this catalyst, it activates the nitroolefin enolate through hydrogen bonding activation, and its tertiary amino moiety activate the nucleophilic thiols, forming an intermediate which undergoes the intermolecular thia-Michael reaction. That means here by using this domino, that means thia-Michael reaction of thiols with nitroolefin. The overall conclusion of this reaction is that here the domino, that means thia-Michael reaction of this thiol with nitroolefin enolates. This is nitroolefin enolates provides the polyfunctionalization, and here we get the highly stereoselective manner, and in the presence of this thiourea catalyst, here we get the three stereogenic center. One is quaternary stereogenic centers generated with high enantioselectivity, and this catalyst, that means this L10, it activates the nitroolefin. When you use this catalyst, thiourea catalyst, it activates the nitroolefin enolates through the hydrogen bonding activation, and here we get the 81% of the yield. Now the synthesis of chiral N-Bock, that means this one, N-Bock beta amino alpha methylene carboxylic acid is formations of or synthesis of N-Bock Bock beta amino alpha methylene carboxylic ester can be performed by the reaction of stabilized phosphorus. That means this one, stabilized phosphorus ylides, and this beta amino N-Bock beta amino alpha methylene carboxylic ester. Okay, that means this one. Here the reaction take place in presence of this L11, that means this organocatalyst, that is thiourea organocatalysts are used, and here the phosphorus ylides is here the reaction between this phosphorus ylides. Now then here, if you write here this PPH3 plus, if you write here delocalize this one, here plus charge and here minus charge, here simple addition, we get the oxygen formation. We know the mechanism, it is similar to the wetting reaction type. Okay, this will be the simple addition. Now then we get this a cyclic compound. Now then cleavage of this one, and here we get this double bond. Okay, now subsequent reaction with formaldehyde provides the facile access to the chiral N-Bock beta amino alpha methylene carboxylic ester, and the catalyst has been found to be the recyclable. That means after completion of this reaction, this catalyst used in the next series of the reaction. That means here the conclusion of this reaction, here this is phosphorus ylide and here the protected amine. Here the simple reaction will be take place between these two. Okay, and here the yield of this product is the 96% enantiomeric excess and 63% yield. By using this catalyst, it activates this imine group, okay, and increase the rate of the reaction. Here the various proportions of the products are given. It is a Manich type reaction of phosphorus ylide. Overall reaction is a Manich type reaction of phosphorus ylide. Now next one is the hydrophosphorylation reaction. Hydrophosphorylation reaction. Here in hydrophosphorylation reaction, here L12, that means this organocatalyst is used, and it is a highly enantioselective hydrophosphorylation of an wide range of N-benzyl imines. Now the hydrophosphorylated products can be readily deprotonated or deprotected by hydrogenolysis using palladium in presence of carbon. That means here these steps, palladium in presence of carbon. Here the NHBN, that means here again a deprotection will be take place. NHBN will be converted into the NH2 groups. Okay, now palladium in presence of carbon provide the chiral alpha amino phosphoric acid with high enantioselectivity. The methodology provides the general and convenient assays for the synthesis of optically active alpha amino phosphonates. That means here the simple reaction, here this is the hydrophosphorylated, okay, here P double bond O, OH, here hydrophosphorylated, and this hydrophosphorylated substrate is on treatment with the L12, that means this is organocatalyst. Here the simple reaction, that means this is imine, C double bond N, that means imine. Here the simple reaction between here, this will be attack on here P double bond O, and here departure of this one group, okay, and here the simple, there is addition of these these groups, it will be directly joined to this phosphorus. Now in next steps, palladium in presence of carbon, here it is a deprotection, okay, that means NHBN, it will convert into the NH2, it is called as a deprotection, okay, and the overall reaction take place in presence of this L12, that means this organocatalyst, and it is called as the thiourea catalyzed enantioselective hydrophosphorylation of imines. This is C double bond N, that means the imine. The practical access to the enantiomerically enriched alpha amino phosphonic acids. That means the conclusion of this reaction, here in hydrophosphorylation reaction, the chiral thiourea catalyst, that means this L12 is used, and it is highly enantioselective hydrophosphorylation of wide range of N-benzyl imine. That means this one, N-benzyl imines. Okay, now this N-benzyl imine, here you on treatment with the this nitro groups. Okay, now the hydrophosphorylated products, that means this one, hydrophosphorylated products can be readily deprotonated. That means these hydrophosphorylated products can be readily deprotonated, or the deprotection will be take place in presence of palladium in presence of carbon, and here we get the 87% yield. Now This methodology provides a general and convenient assays for the synthesis of optically active alpha amino phosphonates. Now, these are the some problems. Try to solve this. Okay. In A, how will you carry out the following using thiourea based organocatalysis? And number B, complete the following reaction. So, friend, try to solve this question. So, friend, never miss a video. Subscribe to my YouTube channel. Okay, thank you.